And now we have lecture 24 on the Brayton cycles, the gas turbines, chapter 9, sections 9.5 to 9.7. Give you a background on gas turbines. They're used in jet propulsion, they're used in power plants. We'll give you the thermodynamic cycle for the gas turbines, and that is going to be the air standard Brayton cycle and also the cold air standard Brayton cycle. And I'll show you a few considerations about work and efficiency. So a quick word of history. This is not very important, but it's always interesting. The Brayton cycle actually didn't start with turbines. It's something that was invented in 1872 as the patent. And they used two cylinders. You have a cylinder here and a cylinder here, one to compress, and there was a combustion chamber, one to expand. Of course, it has been used essentially in jet propulsion as well as in static turbines. Here is one of the very first jet propulsion engines. This was World War II, Juncker-Humo engine with a compressor, combustion chambers, and it powered some of these rather strange-looking jet fighters 70 or so years ago. The more useful, or for the moment, we also use it in stationary power plants. The scale obviously is now much, much more larger. I guess this is a compressor. Here's another compressor. That's a turbine from large stationary engines. So this is both stationary and propulsion. So essentially, we're going to have three main sections in a gas turbine. The first section is this part of the engine. Here's the air intake. This part of the engine is a compressor. It draws air from outside into the engine and pressurizes it. So here's low pressure, there's a high pressure. Then feeds it into the combustion chamber, which is the second system. The combustion system is a ring of things right here. Typically a ring of fuel injectors. They inject a steady stream of fuel into combustion chambers, which I can't quite see on this picture. And the fuel mixes with the air, the high pressure air that comes from the compressor. That then creates a flame that increases the temperature of the gas. The gas in the combustion chamber, of course, is at the pressure at which it was introduced in by the compressor, and it's going to also be the same pressure as we have in the first stage of the turbine, the next stage. But what changes is the temperature and therefore the enthalpy. The third section of a gas turbine is the actual turbine itself. The turbine is here. It's an array of stationary and rotating airfoil blades. They look like airfoils. Hot combustion gases expand through the turbine, spins the rotating blades. Now, these rotating blades then do work on the shaft. That work can be used in either of two ways. Part of the work is used to actually drive the compressor itself. The other part of the work is then the useful work that the turbine will do for the outside world, the net work of the cycle. It can be used, for example, to drive a generator, an electrical generator to make electricity. It can also be used to increase the kinetic energy of the gas, so as to make a jet engine. It can be used to drive a big propeller fan in the front of the engine. So that is basically the balance of the work is the net useful work of the cycle. The thermodynamic model has four processes. We will assume that the working fluid is air. Of course, the air gets mixed with fuel and the fuel gets burnt in the combustion chamber so that the composition in the turbine is different from the composition in the compressor. We will neglect these changes in composition. The other thing that's very important to understand is that here the working fluid is a gas and it's not undergoing a phase change. In the case of vapor power cycles, there are phase changes from liquid to gas. Here not. Everything remains a gas. So the first stage is the compressor. The working fluid is compressed to an elevated pressure, and that compression absorbs work. The temperature at the end of the compressor is higher than the entrance of the compressor because the pressure is higher, and you have this PV as NIT, but you don't know what that's going to be. Second, in the combustion chamber, we add heat to the air. The working fluid is heated to a high temperature, but the pressure in this step is the same as the exit pressure from the compressor. Then the working fluid is sent into the turbine where it generates work. So you now lose both pressure and temperature as it expands and does work. And these are the three stages of the engine. Now, to complete the cycle, we're going to cool the working fluid at a low temperature and reject the heat. Well, so that really can be done in two ways. Well, I lost that graph. That cooling step can be done either by releasing the air outside, and then you will assume that the temperature of the air after a while outside is going to be the temperature of the air at the intake, or it can be done by recycling the turbine exhaust, like in point number 4, through a heat exchanger, cooling it further and sending it back to the compressor. This is another way to close it. So you can either leave this turbine open here and take new air out there, or recycle this air through this heat exchanger. I'm going to assume that these are the two same processes. So to summarize this, step 1 to 2 in the compressor is going to be in an air standard Brayton cycle, which we'll assume ideal in the beginning, an isentropic compression of air, 1 to 2. In a PV diagram, 1 to 2. In a TS diagram, it's 1 to 2 at constant entropy, of course. Number 2, the transition from number 2 to number 3 is in the combustion chamber, injection and combustion of fuel. So we will add a heat Q23 at a constant pressure, because this is assumed to be a heat exchanger. Essentially, the pressure at 3 is the same as pressure at 2, but temperature at 3 will be much higher than temperature at 2. So a PV diagram, pressure at 3 is equal to pressure at 2, but the specific volume will have increased because the temperature has increased. In this TS diagram, you increase temperature and you increase entropy at the same time in following a transformation that's a constant pressure. 3 to 4 is another isentrope. It's the isentropic expansion in the turbine, 3 to 4, or in a TS diagram, it's a vertical line, of course, constant S. 4 to 1 is another heat exchange step, 4 to 1 at constant pressure, either through a heat exchanger that's at constant pressure, or because you reject the air outside, where it's, of course, at the same pressure as the air that comes in. All right, so now let's analyze this a little bit further. Isentropic compression of air, so that means that the work in between 1 and 2, the work change rate per mass of air, is the compressor work rate per mass flow of air, is the enthalpy difference. A turbine or a compressor is an open system, so you work exclusively with enthalpies. The injection and combustion of the fuel adds heat Q23. That heat is equal to the increase in enthalpy between 3 and 2. Isentropic expansion in the turbine is going to be the work done by the turbine in total, is H3 minus H4, and exhaust is modeled as an isobaric heat exchange Q1. Q1 is H4 minus H1. All these systems individually are open, so only enthalpies are used. The network of the cycle, though, is the change of work. It's the work produced by the turbine minus a fraction of it that's absorbed back by the compressor. So that, because it's a cycle, is also equal to the heat in minus the heat out. The efficiency, as usual, is the net work done by the cycle divided by the heat in. So since this is heat in minus heat out, you can work out these equations, use them here. So you replace this Q23 minus Q41 by H3 minus H2 minus H4 minus H1. And you have to divide by Q in, which is H4 minus which is H3 minus H2. So here you're going to have H3 minus H2 minus H4 minus H1 divided by H3 minus H2, which I can simplify to 1 minus H4 minus H1 over H3 minus H2. Back work ratio this time, it's a concept we already introduced in the case of the steam turbines and the vapor the vapor power cycles. So here it's the work of the compressor over the work of the turbine. It's H2 minus H1 over H3 minus H4. If you remember, in vapor cycles, this was on the order of a few percent or fraction of a percent. Here, it's going to be on the order of 30% or more, because we have all a gas. Whereas in a vapor cycle, we had to compress a liquid, and we had to expand the gas. Compressing the liquid takes a lot less work than expanding the gas. So that's the main reason why actually vapor systems are more efficient in general than gas systems. But of course, the details matter enormously. Now, these two processes, isentropic compression of air and isentropic expansion of turbine, are difficult to look up in the tables. It's the same difficulty we encountered when we worked on gas piston engines. And we are going to here again use a trick in the tables. In the case of gas piston engines, which were essentially closed systems, we use the concept of reference volume. Well, here of relative volume. Here we're going to use the concept of relative pressure. We saw this before when we introduced isentropic transformations for ideal gases. But I'll go over it again. So the isentropic transformation between 2 and 1 means that the entropy at point 2 and the entropy at point 1, this is a 1, this P2 is P1, is the same. Well, but we know that entropy in an ideal gas depends on temperature and on pressure. We can tabulate the entropy changes at a constant pressure, at a given reference pressure, when we do this for a certain temperature, that's S0, but we can then have to add a correction factor for the changes in pressure. So S2 minus S1 is really S0 of T2 minus S0 of T1 minus R log of P2 over P1. In an isentropic transformation, that is this thing with three terms is what we have to set to 0. So now we end up looking up in our tables both T2 and S0 of T2 and T1, but also we need to know the ratio of change of pressures, which becomes then very quickly an equation with two equations with two unknowns. There is a trick that is applicable to air only, and that is instead of just tabulating S0, which is done in table A22, you tabulate a variation of H0 called the relative pressure. It's a trick. So how do we do this? Well, to solve this equation here, and that the solution to that equation is to write, well, you just have to put this on the other side, then take the exponential everything to invert the logarithm. And this equation between here and here is the same as writing P2 is P1 exponential of S0 of T2 minus S0 of T1 over R. So you can look these up and then solve. But there is an easier way, and that is to define PR, this is now your relative pressure, as exponential of S0 over R. Because if you do that, you have P, so this term then becomes PR2, and a minus in the exponential means in reality you divide by. So this term is PR1. So you rewrite this equation, P2 over P1 is exponential of this first term. Divide by exponential of this second term, that's distributing the exponential across the difference. And this now, if you can recognize in here, PR2 over PR1. So you have P2 over P1, PR2 over PR1. These are tabulated. That means it's very easy for you now to find P2 as a function of P1. So it's a trick. Careful, it is not a pressure. PR2 is not a pressure. It only works when you work with air. It only works for isentropic transformations, and it simplifies the lookup tables. It's redundant with using S0 of T. It makes the calculations easier, but it's not necessary, really. And computers, if you look up tables or computer software, it never does that. It just does it directly. Now, we can go over the steps in the Brayton cycle, in the air standard Brayton cycle. You can take your first isentropic transformation of air, and the recipe is PR2 is PR1, P2 over P1. You have your injection of heat, Q23, that's going to be H2 minus H3. So if you know your state 1, you find H1, PR1, and you have P1, that's known. So if you then are given, for example, P2, and that's very often the case because a crucial design parameter of a Brayton cycle is the ratio P2 over P1, which is beta, which is a compression ratio. Then you can find PR2. Again, in your tables, once you have PR2, you have all the other properties of the air because they don't depend on pressure. So you can find T2, H2, etc., which you can plug in here. Then you're going to be given something else, like the heat in or your temperature, to find H3. And then you have the isentropic expansion in the turbine, which has the same equation. PR4 is PR3, P4 over P3, which P4 over P3 given the system, which is only pressure changes happen in compressor and in turbine, no pressure change in the heat exchangers. P4 over P3 is P1 over P2, which is also your compression ratio. So now if you have the properties of point number 3, P3, PR3, you can find the properties of point number 4. And then 4-to-1 exhaust is modeled as an isobaric exchange at Q41. Okay, let's take a simplified cycle just so we can show you a few basic principles, but that's a cold ideal air standard cycle. The cold air standard cycle, to repeat, assumes that Cp and Cv do not change with temperature, and so here is an equation that mixes, they're missing. That is the definition of lowercase k, which we find here. K is the ratio of Cp over Cv by definition. Now, in the Brayton cycle, the cold air standard analysis is not particularly applicable because temperature differences will scale from 300 Kelvin to 1800 Kelvin or even 2000 Kelvin. And over such a very wide temperature range, it's sort of pushing things very high to say that Cp and Cv are not temperature dependent. They are. So this is an approximation, but it will greatly simplify the equations because now we can say that the isentropic compression of air, T2 is T1 P2 over P1 over this ratio, K minus 1 over K. We have derived this when we looked at isentropic transformation in chapter 6. And the same, T4 is T3 P4 P3, which is of course P1 over P2, K minus 1 over K. So these equations are very, very much simpler than the equations where we had to look up the relative pressures. They're not terribly accurate, but we will use them for a quick and convenient analysis. Here is the equation that I should have had on the previous page. So from this, we can derive that T4 over T1 is T3 over T2. So what you have here, the ratio between these two equations, you see T2 is T1, P2 over P1, K minus 1 over K, and here you have, actually you have T3 is T4, that's P2 over P1, K minus 1 over K, so T4 over T1 is T3 over T2. This is the slide that I wanted. The previous slide was not necessary. All right. Now we plug this in, the equations for work and for heat. So W12 is H2 minus H1. H is simply Cp times T because Cp is constant with temperature. So it's Cp T2 minus T1. Q23, Cp T3 minus T2, H3 minus H2. W34, Cp T3 minus T4. And Q41, Cp T4 minus T1. These are all just enthalpies. Okay, so that means that Wc over m can be rewritten as a function of this compression ratio. Beta is P2 over P1, it's T2 minus T1 minus 1, which is T1, take T1 out of the parentheses. This is beta K minus 1 over K, as we've seen for the isentropic transformations in the previous equation, minus 1. We can do the same for the turbine. It's Cp T3 1 minus beta over minus K minus 1 over K. Look at your previous equations, this comes out to be okay. And therefore, your efficiency, which is simply the difference between these two divided by Q41, turns out to be 1 minus T4 minus T1 over T3 minus T2. You can take T1 over T2 outside this equation, and you have then ratios of T4 minus T1 over T3 minus T2. You can derive your efficiency from just temperatures. That's nice. That means you can also replace it by simply this compression ratio, beta. Beta is P2 over P1. And now we can make this plot of efficiency versus beta. Efficiency is 0 when beta is 1. That's okay. Beta is 1 means you have a compressor that does nothing. Inlet air is the same pressure as outlet air, therefore nothing works. But this just tells you that if you had just a combustion chamber, you made a little fire, you connected that to a turbine, your turbine wouldn't rotate. Okay, very good. But then as you increase this compression ratio, your efficiency increases gradually. So once again, higher compression ratio, actually this is a carbon copy of what we said in the piston-driven engines, but of course in piston-driven engines, compression ratio actually means volume ratio. Here in turbines, it means genuine compression ratio. And so the higher the compression ratio, the higher the efficiency. That sounds great. Now, there are a few glitches with this whole thing, which are related to the fact that we are using cold air analysis, which we shouldn't. The first bizarre thing is that there is no temperature in this. It would mean that you could design your turbines just with pressure ratios alone, ignoring temperatures. That is unphysical because, of course, Carnot tells you that the most important thing in a thermodynamic cycle is the ratio between the higher temperature and the lowest temperature, which doesn't seem to enter this equation, so that's strange. Of course, it did enter the previous equation. Here, this is very clearly an expression of Carnot, but it's a fact that these temperatures are uniquely related to this compression ratio. That is a bit strange, and it's really due to this extremely simplifying assumption we made that Cp and Cv are not temperature dependent. Nevertheless, it gives you a good indication that the higher the compression ratio, the better your turbine is going to be. And with that, I am at the end of this lecture. Thank you.